brief idea how the vote is. Suppose this is a ball and we have to send vote here. Okay, this is the receiver at point B. We already know that if this is a strict tensor, okay, we can vote here. And the formula is in the form of SSO. Okay. If I rotate it, this will be another strict tensor of eigenvalue 1. It can vote here. It can vote here. So we are just rotating our stick and we are getting some eigenvalue here. So he is just trying to integrate this one by rotating the disk, by rotating this one from angle 0 to 1. And R theta is rotation matrix aligned to S with E1. Now we got the V, the voting value due to ball and due to the stick. What will the final voted value? This will be the, either you can say integration or you use summation of all the votes. Just if you sum all the votes, you are at a point, you are getting the votes, you are just doing the summation, you will find the final eigenvalue or the tensor value. In this manner, you can get the output. Now he is talking about voting fields. It's the same as electric field. As I told you, initially when we started studying about electricity, if you remember, we find out electric field due to one charge at some point. Okay, then we take 2 and find out what the direction of this one. Slowly the discrete values increases and it becomes electric field. Similarly, in an image, what is happening? If you are trying to vote from all the points, initial level you will try to take 1 point, 2 point, 3 point, you will get the formula for one, and at last what will say? Like electric field here, you will say voting field here, which is the integration of all the voting values. So votes from both stick and ball voters cast at receivers at various distances and angles were pre-computed and stored in voting fields. This is the last line is very important to understand, that all our sticks and balls which are in the neighboring node, they are already calculated and put in a stored in a voting field. So these are the results in 2-dimensional. As I showed you earlier. So in this manner, we extract image from the data which was noisy, but I was talking about 2-dimensional. The same thing in 3-dimensional. In 3-dimensional, E1, E2 and the third eigenvalue is, eigenvector is E3, and it is changed, the presentation is little bit changed to show the basic thing. In 3-dimensional, we have stick, we have disk, and we have ball. If this kind of input is there, how the stick tensor will become, or the plate tensor becomes with different eigenvalues. I can explain these things, but I think you are getting what I'm trying to explain. And this is the final, how to extract the image from the points. I think you are getting the basic idea of it. How will do the tensor voting? Yes.
Have you ever compared this method with other methods, especially the time?
No, the thing is that here the important point I studied, everything you are extracting not by imagination, you are getting from the data. The data is coming and it is automatically going to machine language and it's calculating the things and getting out the images. Normally what happens, suppose some image is there, so by physical sense you say, oh, this may be this figure. So you start with a minimum figure and there is possibility of error. But here everything is based on data. Let me show you its main advantage. No, I didn't compare with anything, but I studied.
You don't know any comparison?
I know the comparison, but as I told you, these are the different methods. I just wrote it here. I have all the methods explanation for this one, but I didn't went into that one. So symbolic method, method based on local. But the major difference between tensor voting and other methods is solution emerges from the data. That's the more important. The data is directly fed into the algorithm.
I think for even you can use this for the noisy and maybe finding a clear edge. But I think the effect, the time. Yeah, because you, as you said, you must for the voting, you must pull up the point.
Look, and, yeah, you can say, but the thing is that you have to, you can say, it's noise robust. So somewhere you have to take some advantage and you have to leave some disadvantage, like here time. If you say time is more, then you have to play with the things.
You didn't any didn't see any comparison this method and another method, any papers?
Honestly speaking, I didn't study those papers because here the problem was I never studied tensor earlier, and developing a concept of new things like tensors, it was a big time consuming, and image processing was new for me, so everything was which I'm studying is new. That was the reason I didn't went.
This is a proof for Dr. Cheng that we were all here.
I see there's an image. It's noisy, diluted noise. It is from the paper.
Yeah.
And this is one application of the noisy quality processing. Can I see that?
Just a minute. Are you talking about this one?
Yes.
Yeah.
Can we say denoising is one application for the resolution? Can you say this denoising process could be a application? Is there any other application that author mentioned?
I have studied tensor routing 7 papers. In every paper, they were using for the same application. And but in this application, they are using some filters or some different things. But the main application is this one.
This one?
Yeah.
Okay.
The image.
Oh, go ahead.
If we go to the next slide.
Next one.
Next one. There's a ball.
Oh, this one?
No, this one. Oh, yeah. But this one looks like noise on the right side.
In the C1 or in the first A and B?
This is the first one.
C, originally.
Yeah.
But this one looks like noise, but after that, it's not like noise.
Yeah, it seems to me, but I took it as it from the paper, this figure, and it says that input is in this format, but output is kind of a ball. So he mapped it into some not in form of surface, you can say. But yeah, you are right. Even it was looking to me, but I took it from the paper as it is. So
Seems the result depends on the parameter you choose. Right?
yeah, you are right. Yeah.
But it's like arbitrary, like subjective, so you don't know what's actually in the picture, but you choose some parameter.
As I told you, I didn't use any program for this. I just read the paper and I took the values which is given on this one.
So, do you want to conclude before we end this?
Yeah, concluding is that yes, please.
Yeah. Give me a point on that question.
Huh?
Give me a point here.
Okay. Like it's all based on a machine language program. It is in the. I have studied the thesis, but I didn't check the program. Suppose we are getting some points like this. Now what happens? This is an input token, this is input token. So what will happen? We'll receive input token and it will start voting. And after that one, we will find, okay, there should be some kind of curve here. So it goes something like that.
So how to represent a point in tensor?
Yeah.
Tensor, oh, point is nothing.